There is a galaxy you can see with your own eyes on a clear, dark night. It appears as a faint smudge of light in the constellation that shares its name. A soft, elongated patch, sitting quietly among the stars. Easy to overlook. Easy to mistake for nothing more than a distant cloud. Most people who notice it do not stop. They look past it towards something brighter, something more obvious. But that faint smudge is one of the most extraordinary things visible from Earth, without any instrument at all. It is not a cloud. It is not a region of our own galaxy. It is another galaxy entirely. A vast, separate structure containing roughly 1 trillion stars, sitting 2.5 million light-years away in the darkness of intergalactic space. And its name is Andromeda. Welcome to Sleepy Time Universe, where we explore the cosmos at a pace designed for rest and reflection. Tonight, we are going to sit with Andromeda slowly and without hurry. We will look at what it actually is, its size, its structure, its age, the stars burning inside it, the darkness surrounding it, and the almost incomprehensible distance that separates it from the world you are lying in right now. We will think about how we came to know what we know about it, and what those numbers genuinely mean when you take the time to let them settle. We will follow Andromeda from its visible edge all the way inward to the enormous concentration of matter at its center. And we will think about what its existence says about the scale of the universe we all share. There is no need to rush. The galaxy has been there for 12 billion years. It will wait for us to take our time. Chapter 1. The distance between us. The first thing to understand about Andromeda is how far away it is. Not in a general sense, not simply that it is very far, but in the specific, careful sense of what that distance actually means for light, for time, and for any attempt to think about it honestly. Andromeda sits 2.5 million light-years from Earth. A light-year is the distance light travels in 1 year, moving at approximately 186,000 miles per second. In a single second, light crosses a distance roughly 7.5 times the circumference of the Earth. In 1 year, it covers about 5.9 trillion miles. 2.5 million of those years of travel represents a number that contains no simple analogy, no everyday comparison that holds its shape under examination. It is a distance so large that the word large has stopped carrying any useful meaning. But we can approach it in stages. The Sun is approximately 93 million miles from Earth. Light from the Sun reaches us in about 8 minutes and 20 seconds. If the Sun were to disappear at this moment, we would continue to see it for another 8 minutes before the last of its light faded. The Moon is much closer, roughly 250,000 miles away, and light from it reaches us in just over 1 second. These are distances a human mind can almost hold, if not quite grasp. The nearest star beyond our Sun is Proxima Centauri, about 4.25 light-years away. Light from Proxima left its surface more than 4 years before it reaches your eye. When you look at that star on a dark night, you are seeing it as it was 4 years ago. The star has continued burning since then, and the light from those burning moments is still traveling toward you. It has not arrived yet. Andromeda is not 4 light-years away. It is not 40. It is not 4,000 or 400,000. It is 2.5 million light-years away, which means the light entering your eye when you look at that faint smudge left Andromeda 2.5 million years ago. It has been traveling through the emptiness of intergalactic space, across a void with no stars, no planets, no gas worth speaking of, just the darkness itself, for a span of time that encompasses the entire existence of our species, and then a great deal more. 2.5 million years ago, there were no modern humans on Earth. There were early members of our genus, beings who walked upright, who used simple stone tools, who lived in small groups on open grassland, but nothing we would recognize as civilization, nothing we would call language in any complete sense. The entirety of recorded human history, from the first cities to the present day, represents less than 1/5 of 1% of the time that light from Andromeda has been in transit. Every empire that has ever risen, every language ever spoken, every piece of music ever composed, all of that has happened during what amounts to the final fraction of Andromeda's light's long journey to us. This is not a metaphor for scale. It is the literal situation. The distance also carries a quiet consequence that is easy to miss on first consideration. When you observe Andromeda, you are not seeing it as it is now. You are seeing it as it was 2.5 million years ago. Its present state, whatever is happening in its spiral arms and at its center tonight, in its own reference frame, is completely unknown to us. That information has not yet arrived. It is on its way, traveling at the speed of light, and will not reach Earth for another 2.5 million years. We are looking at the past. We are always looking at the past when we look at anything. But with Andromeda, the past is so deep that it exceeds the entire span of human existence on this planet. There is something quietly steadying about that fact, once you sit with it. The galaxy does not know we are looking. It does not know we exist. It was there long before us, burning through its slow cycle of stellar births and deaths, and it will continue long after. We are small observers at a great distance, watching light that left its source before anything we would call human had yet appeared on Earth. The vastness of that distance is the foundation of everything else we will discuss tonight. Every number, every structure, every detail about Andromeda sits on top of that fundamental fact. 2.5 million light years of empty space between us and the nearest large galaxy. A gap that no human being, no machine, no signal we have ever sent has come close to crossing. Chapter 2. What Andromeda actually is. Before thinking about what sits inside Andromeda, it is worth establishing what kind of thing it is, not just a galaxy in the general sense, but a specific type of structure with a specific shape and a specific arrangement of matter that has developed over billions of years through processes we now understand reasonably well. Andromeda is a barred spiral galaxy. This means it has a disk of stars and gas arranged in a flat, rotating plane, with arms of denser material curving outward from a central region in a loose spiral pattern. At the very center, rather than a simple spherical concentration of old stars, there is an elongated bar-shaped structure, a thickening of the disk that channels how material moves through the inner galaxy. Both Andromeda and our own Milky Way share this basic architecture, which is one of the reasons comparing them tells us so much about how large spiral galaxies in general are built and how they age. The disk of Andromeda spans approximately 220,000 light years from one edge to the other. To cross it at the speed of light, the fastest speed physics permits, would take longer than modern humans have existed as a species. Our own Milky Way stretches roughly 100,000 light years across. Andromeda is substantially larger, roughly 1.5 times the diameter of our own galaxy, and it contains somewhere in the region of 1 trillion stars. The Milky Way, by comparison, holds somewhere between 100 billion and 400 billion stars, depending on how the count is made and which regions are included. Andromeda's stellar population is 2 to 3 times our own. 1 trillion stars. The number is stated easily enough, but it does not carry its own weight without some attempt to feel the size of it. If you counted 1 star per second without pause, no sleep, no rest, no interruption of any kind, you would need approximately 32,000 years to finish. That span is longer than the entire history of human civilization, from the earliest settled communities to the present day. Every city ever built, every dynasty ever recorded, every century of art and language and agriculture, all of that time would not be enough to count the stars in Andromeda one by one at a rate of 1 per second. The total mass of the galaxy, including all of its stars, the gas and dust distributed between them, and the vast envelope of dark matter that surrounds it and holds it together, is estimated at somewhere between 1.5 and 2 trillion times the mass of our Sun. Most of that mass is invisible. The stars and gas that produce light account for only a fraction of the gravitational influence we detect when we measure how the galaxy rotates. The rest is dark matter, a form of matter that does not emit or absorb light in any wavelength we have yet detected, but whose gravitational presence is unmistakable in the motion of everything visible around it. We will return to dark matter later. For now, the important point is that Andromeda is considerably more massive than it looks, and what it looks like is already enormous. The shape of the galaxy is not simply a flat disk, it is more layered than that. At the center sits a large, rounded bulge, a roughly spherical concentration of old stars that spans about 30,000 light-years across, which is nearly 1/3 the diameter of the entire Milky Way. The bulge contains several 100 billion stars packed into a relatively small volume compared to the disk. Stars here are far older than the Sun and carry far fewer of the heavier elements that form rocky planets and living organisms. They belong to a different generation of stellar history, matter that condensed and ignited in the early universe, before most of the galaxy's chemistry had developed. Beyond the bulge, the disk extends outward in a gradually thinning sheet. It is remarkably flat relative to its width, roughly 1,000 light-years thick at the regions corresponding to our own position in the Milky Way, spread across a diameter of 220,000 light-years. The flatness is a consequence of rotation. As the galaxy formed, the gas that would become the disk collapsed inward while spinning, and the spinning flattened it the way a ball of dough flattens when rotated. What remained was a thin, turning plane of stars and gas, with the spiral arms visible as regions of slightly higher density winding outward from the bar. The spiral arms themselves are not rigid structures. They do not rotate with the disk the way spokes rotate with a wheel. Instead, they are waves, patterns of compression that move through the disk at a different rate than the individual stars. Stars and gas clouds pass through these arms during their orbits around the galactic center, spending time inside the denser region before continuing outward. The arms appear bright because the compression they produce tends to trigger the formation of new stars, and newly formed massive stars are intensely luminous. They burn brilliantly in blue and ultraviolet light for a few million years before exhausting their fuel and exploding, which is why the arms glow with the color of youth, while the older regions of the disk and the bulge carry the warmer reddish tone of stars that have been burning for billions of years. Andromeda's spiral pattern is not perfectly symmetrical. One side of the disk is more prominent than the other, and the outer regions of the gas disk are warped, tilted slightly away from the plane of the inner galaxy. These asymmetries are the visible residue of ancient events. Roughly 800 million years ago, Andromeda experienced a significant collision with another large galaxy, That collision disrupted the orderly structure, introduced distortions that have not yet fully resolved, and left behind the kinds of uneven features we observe today. A galaxy of this size recovers from such an encounter on timescales of billions of years. Andromeda is still settling. There is also a prominent ring of enhanced star formation located about 32,000 light-years from the galactic center. This ring appears in ultraviolet observations as a concentration of young, hot stars. Thousands of stellar nurseries active simultaneously, each one a dense cloud of gas in the process of collapsing under its own gravity and igniting. The ring's origin is connected to the bar structure at the center, which influences how gas distributes itself through the inner disk, creating regions of accumulation at certain distances where the conditions for star formation are particularly favorable. Around the disk and the bulge, extending far into the space surrounding the visible galaxy, lies a roughly spherical halo of older stars and globular clusters. This halo is faint and diffuse, containing only about 1% of the galaxy's total stellar mass, but spread across a volume that dwarfs the bright disk. The halo extends to at least 500,000 light-years from the center, more than twice the radius of the visible galaxy. Stars out there are separated from their nearest neighbors by distances far greater than the roughly 4 light-years between the Sun and Proxima Centauri. In Andromeda's outer halo, a star might spend most of its existence hundreds of thousands of light-years from the galaxy's center, drifting through near-total darkness with the faint glow of the galactic core visible at an enormous distance. What lies at the very center of all this structure is something we will look at more carefully in a later chapter. For now, it is enough to know that at the heart of Andromeda's bulge, surrounded by billions of old stars packed into a relatively small region of space, there is a supermassive black hole with a mass of approximately 140 million times the mass of our Sun. By comparison, the black hole at the center of the Milky Way, known as Sagittarius A star, has a mass of around 4 million solar masses. Andromeda's central black hole is roughly 35 times more massive. It sits quietly at the moment, not actively consuming large amounts of material, but the potential is there, and we will think about what that means in time. Chapter 3. How we know how far it is. One of the most reasonable questions to ask about Andromeda is also one of the most fundamental. How do we actually know it is 2.5 million light-years away? The number is stated with confidence in textbooks and documentaries, but the method behind it is not always explained, and the method matters. Distance measurement in astronomy is not a single technique applied once and confirmed. It is a careful construction, a series of methods built on top of one another, each one reaching a little further into space than the last, each one dependent on the reliability of the steps below it. Astronomers call this construction the cosmic distance ladder. The lowest rung of that ladder begins close to home, within our own solar system. For nearby objects, the Moon, the planets, nearby asteroids, distance can be measured directly using radar. A radio pulse is sent outward, it bounces off the target, and the time it takes to return tells us the distance precisely. This method works well within the solar system because the distances are small enough that the signal returns in a measurable time, and the round trip can be timed accurately. For slightly greater distances, nearby stars within a few thousand light years, astronomers use a geometric method called parallax. As Earth moves around the Sun over the course of a year, nearby stars appear to shift slightly against the background of more distant stars, in the same way that a finger held close to your face appears to move against the far wall when you alternate closing each eye. By measuring the size of that apparent shift and knowing the diameter of Earth's orbit, the distance to the star can be calculated using straightforward trigonometry. The method is reliable and precise, but it has a limit. Beyond a few thousand light years, the shifts become too small to measure accurately, even with the most sensitive instruments we have built. For greater distances, a different approach is needed. This is where standard candles come in. A standard candle is any object whose true brightness is known. If you know how bright something actually is, and you measure how bright it appears from your position, the difference between the two tells you how far away it must be. The principle is simple. The same light source appears dimmer the further away it is, in a precise mathematical relationship. A source 4 times further away appears 16 times dimmer. By knowing the true brightness and measuring the apparent brightness, the distance follows directly. The most important standard candles for measuring distances to nearby galaxies are a type of variable star known as Cephids. Cephids are large, luminous stars that pulsate, growing brighter and dimmer in a regular cycle that repeats over days or weeks. The critical discovery, made by astronomer Henrietta Swan Leavitt in the early years of the 20th century, was that the period of a Cephid's pulsation is directly related to its true luminosity. A Cephid that takes longer to complete each cycle is genuinely more luminous than one with a shorter cycle. Measure the period, and you know the true brightness. Compare that to how bright the star appears from Earth, and you have the distance. This discovery transformed astronomy. It gave astronomers a reliable ruler for measuring distances far beyond what parallax could reach. Edwin Hubble used Cephid variables in the 1920s to measure the distance to Andromeda, working with the largest telescope then available at Mount Wilson Observatory in California. By identifying individual Cephid stars within the faint smudge and measuring the timing of their brightness cycles, he calculated a distance that proved Andromeda was not a nearby cloud of gas within the Milky Way, as many astronomers had assumed, but an entirely separate galaxy existing far beyond the boundaries of our own. His initial estimate was an underestimate. He did not yet know that there are 2 distinct types of Cepheid stars with different period luminosity relationships, and he was working with the less luminous variety without realizing it. But the conclusion was correct and revolutionary. Andromeda was another island of stars, an entire galaxy, separated from ours by an almost unimaginable gulf of space. Modern measurements, made using the Hubble Space Telescope and incorporating a more refined understanding of Cepheid types and calibration, have settled the distance at 2.54 million light-years, with an uncertainty of only a few %. That level of precision, for an object so remote, required decades of careful observation and the gradual refinement of each rung of the distance ladder. For galaxies further away than Andromeda, too distant for individual Cepheid stars to be resolved even by the most powerful telescopes, astronomers use even brighter standard candles. A particular type of stellar explosion known as a Type 1. A supernova produces a flash of light at a remarkably consistent peak brightness, bright enough to be seen across billions of light years, because we know roughly how bright these explosions actually are, and we can measure how bright they appear from Earth. They serve as distance markers at cosmological scales. The Cepheid distances to nearer galaxies are used to calibrate the supernova distances to farther ones, which is why the accuracy of the Andromeda measurement has implications that extend across the entire observable universe. Andromeda occupies a particular position on the distance ladder, close enough to measure with Cepheids directly, and important enough as a nearby spiral galaxy that its distance serves as a calibration point for measurements reaching far deeper into space. Getting Andromeda's distance right is not just a matter of knowing where our nearest large neighbor is. It is part of the foundation on which our understanding of the entire large-scale structure of the universe rests. There is something worth pausing on in all of this. The methods described here were built entirely from within the Milky Way, by observers who had never left the Earth, using instruments pointed at objects they could never visit. The distance to Andromeda was not measured by traveling there and looking back. It was reasoned out, step by careful step, from observations of brightness and timing made by people sitting on a small planet in an unremarkable part of one galaxy, looking outward into the dark. The fact that those measurements are accurate to within a few percent, verified by multiple independent methods using different physical principles, is one of the quieter achievements in the history of human knowledge. The distance is real, the methods are sound, and 2.5 million light-years is not an estimate in any casual sense. It is a measurement carefully earned. Chapter 4. The Stars Inside. 2.5 million light-years away, inside a structure 220,000 light-years across, there are approximately 1 trillion stars. Each one is a sun. Each one is a sphere of gas held together by its own gravity, generating energy through nuclear fusion in its core, radiating light and heat outward into the space surrounding it. Some are larger than our sun. Many are smaller. Some are very old, and some are very young, and the full range of stellar ages and sizes and temperatures present inside Andromeda tells a story about the galaxy's history that is written in light if you know how to read it. The most fundamental thing about a star is its mass. Mass determines almost everything else: how bright the star is, how hot its surface runs, how long it will live, and what it will become when its fuel runs out. This is not a loose correlation. It is a precise and well-understood relationship that governs stellar life from birth to death, with very little variation. The smallest stars are called red dwarfs. They contain less than about 40% of the sun's mass, and they burn their hydrogen fuel so slowly and efficiently that their lifespans extend to trillions of years, far longer than the current age of the universe. Every red dwarf that has ever formed anywhere in Andromeda is still burning today. Not one has had time to die. They are the most common type of star in the galaxy by a very large margin, making up the overwhelming majority of Andromeda's stellar population numerically, but contributing relatively little to its total light output, because each one is individually faint. To see a red dwarf in Andromeda directly, you would need an instrument far more powerful than anything currently built. We know they are there because we understand how star formation works and because the total mass of the galaxy requires them. But they remain individually invisible to us at this distance. Stars of intermediate mass, similar to our sun, live for billions of years. The sun has been burning for about 4.5 billion years and has roughly another 5 billion years remaining before its core hydrogen is exhausted. At that point, it will begin to change in ways that are slow by human standards, but dramatic in astronomical terms. The core will contract and heat, while the outer layers expand outward, swelling to many times the sun's current size. It will become a red giant, a cooler, vastly larger version of itself that will eventually shed its outer layers into space in a slowly expanding shell of glowing gas. What remains at the center will be a white dwarf, a dense, slowly cooling remnant roughly the size of Earth, but containing most of the original star's mass. White dwarfs cool over trillions of years, gradually fading toward darkness. Massive stars, those born with more than about 8 times the mass of the Sun, live very differently. They are intensely luminous, burning through their fuel at rates that leave them only a few million years of life. A star 20 times the mass of our Sun may live for 10 million years or less, which is an almost negligible span compared to the age of the galaxy. These stars shine brilliantly in blue and ultraviolet light, and their presence in the spiral arms of Andromeda is part of what gives those arms their distinctive bright appearance. When a massive star exhausts its core fuel, it does not fade gradually. It collapses and then explodes, a supernova, releasing in a matter of weeks an amount of energy comparable to what the Sun will emit over its entire 10 billion year lifetime. The explosion blasts the star's outer layers outward at tens of thousands of kilometers per second, seeding the surrounding interstellar space with the heavier elements forged in the star's core during its life and in the explosion itself. These heavier elements, carbon, oxygen, silicon, iron, and dozens of others, are what make rocky planets possible. They are what make living chemistry possible. The first stars in the universe formed from almost pure hydrogen and helium, with essentially nothing heavier present. When those early stars died, they returned enriched material to the space around them. The next generation of stars formed from gas that included those heavier elements, and when those stars died, they enriched the medium further. Each generation of stellar birth and death has gradually increased the chemical complexity of the galaxy, building up the inventory of heavy elements that now allows planets like Earth to exist and allows the chemistry of life to operate. In Andromeda, right now, all of these processes are happening simultaneously. Red dwarfs are burning steadily in their billions, unchanged from the moment they formed. Middle-aged stars like the Sun are fusing hydrogen quietly in their cores. Red giants are swelling and cooling in the later stages of their lives. Planetary nebulae, the glowing shells of gas shed by dying medium-mass stars, are expanding through the interstellar space around newly exposed white dwarfs. And massive stars, somewhere in the galaxy's spiral arms, are collapsing and exploding as supernovae at a rate of perhaps 2 or 3 per century. Each explosion enriches the surrounding gas, compresses nearby clouds, and sometimes triggers the formation of new stars in the regions where the shock wave passes. The stellar population of Andromeda is not uniform in age or composition across the galaxy. The oldest stars are concentrated in the bulge and in the halo, the rounded, spherical regions above and below the disk. These are population 2 stars, formed in the early history of the galaxy when the universe was young and the interstellar medium had not yet been significantly enriched by previous generations of stellar death. They contain relatively few heavy elements, which makes them chemically distinct from younger stars and gives them a reddish color that contributes to the warm glow of Andromeda's central regions when viewed through a telescope. The younger, heavier element-rich population 1 stars are found primarily in the disk and spiral arms. These are the stars born from gas that had already been processed through multiple generations of stellar life and death, gas that carried the accumulated chemistry of billions of years of stellar evolution. Stars like our Sun belong to this population. They are enriched enough to have formed rocky planets, and those planets are enriched enough to support the kind of complex chemistry that, on at least one world in one galaxy, eventually produced living things capable of looking outward and wondering about distant galaxies. About half of all stars in Andromeda, as in most galaxies, are thought to exist in binary or multiple systems, pairs or small groups of stars orbiting a shared center of mass. Binary systems introduce additional possibilities for stellar evolution that single stars do not have. If one star in a pair evolves into a white dwarf, while its companion is still on the main sequence, the white dwarf can gradually pull material from its companion through gravitational attraction. If enough material accumulates on the white dwarf's surface, the conditions can be reached for a runaway thermonuclear explosion, a Type 1a supernova, the same class of explosion used as a standard candle for measuring cosmological distances. The fact that these explosions happen at a fairly consistent peak brightness is connected to this process of accumulation, reaching a critical threshold. Andromeda produces roughly one such explosion every few hundred years on average. All of this stellar activity, the births, the long stable lives, the various forms of death, contributes to an ongoing cycle of matter through the galaxy. Gas collapses into stars. Stars process that gas through nuclear fusion, building heavier elements. Stars return that processed material to the interstellar medium through winds, planetary nebulae, and supernovae. The enriched gas mixes with fresh material and eventually collapses again into new stars. The cycle has been running in Andromeda for approximately 12 billion years, and it continues tonight, invisible to us at this distance but real and ongoing in the galaxy's own present. Chapter 5. The Heart of the Galaxy. At the center of Andromeda, surrounded by the densest concentration of stars in the entire galaxy, there is a region unlike anything in our immediate neighborhood. The central bulge alone spans 30,000 light-years across, a rounded, ancient structure packed with hundreds of billions of old stars, their combined light creating a permanent glow that would make true darkness impossible for any observer situated anywhere near the galactic core. But at the very heart of that bulge, hidden within the innermost region, where the stellar density reaches its peak, sits something far more extreme than any star. A supermassive black hole with a mass of approximately 140 million times the mass of our Sun. To place that number in context, the black hole at the center of our own Milky Way, Sagittarius A star, one of the most studied objects in modern astronomy, has a mass of roughly 4 million solar masses. Andromeda's central black hole is approximately 35 times more massive. It is one of the larger central black holes known among nearby galaxies, a genuinely enormous concentration of matter compressed into a region of space smaller than our solar system. A black hole of this mass does not look like anything from the outside. It has no surface, no edge that light can bounce off and return to an observer. It has a boundary, the event horizon, which is the point of no return, the distance from the center at which the escape velocity equals the speed of light. Anything that crosses that boundary, whether matter or radiation, is gone. No signal can return from beyond it. The event horizon is not a physical surface. It is a geometric fact about the structure of space-time in that region, a consequence of how gravity curves the space around an extreme concentration of mass. From outside the event horizon, the black hole makes itself known only through its gravity and through what happens to material that comes close to it without quite falling in. Gas and dust drifting into the vicinity of the black hole are captured into an orbiting structure called an accretion disk, a flattened, spiraling ring of material gradually losing energy and angular momentum as it works its way inward. As material in the accretion disk falls toward the event horizon, it is compressed and heated to extreme temperatures, radiating intensely across multiple wavelengths. The innermost regions of an active accretion disk can reach temperatures of millions of degrees, producing X-ray emission detectable across enormous distances. Andromeda's central black hole is not particularly active at present. It is not consuming large amounts of material. There is no significant accretion disk currently forming around it, no bright jet of particles being launched outward from the inner disk region, no intense radiation pouring from the galactic center at levels that would be visible from Earth. The black hole is, in the language astronomers use, quiescent, quiet, waiting, not doing much of anything detectable at the moment. But this state is not permanent, and it is not guaranteed. The conditions that keep the black hole quiet are simply the absence of material falling toward it in sufficient quantities to trigger active accretion. If a dense gas cloud were to drift into the innermost region of the galaxy and begin spiraling inward, or if a star were to pass close enough to be disrupted by the black hole's tidal forces, the situation would change. A star venturing too close would be stretched and torn apart in what astronomers call a tidal disruption event. The black hole's gravity pulling more strongly on the near side of the star than the far side, shredding it into a long stream of gas that wraps around and begins to spiral inward. The energy released as that material falls toward the event horizon would produce a flare of radiation visible across millions of light years, briefly transforming the galactic center into one of the most energetic sources in the local universe. Such events happen occasionally in galaxies throughout the universe. Astronomers have observed them in distant galaxies as sudden brightening events in galactic nuclei that were previously quiet. They are transient. They fade as the disrupted material is consumed or expelled. But while they last, they are extraordinary. Andromeda's central black hole has almost certainly produced such events in its past, and will produce them again in the future. On the timescales relevant to the galaxy's life, the current quiet period is simply one phase among many. The stars surrounding the black hole in the innermost regions of the bulge exist in an environment that has no parallel anywhere near our solar system. The stellar density close to the galactic center is thousands of times higher than in the neighborhood of the Sun. Stars here are separated from their nearest neighbors, not by light years, but by far smaller distances. Close gravitational encounters between stars are common by astronomical standards. Binary systems can be disrupted, with one star captured into a new pairing, and the other flung outward at high velocity. Occasionally, a star is accelerated enough by such an encounter to escape the galaxy entirely, becoming what astronomers call a hypervelocity star, a rogue object moving through intergalactic space with no galaxy to call home. The old red giant stars that dominate the central bulge carry within their composition a record of the galaxy's early history. They formed from gas that had undergone relatively little chemical enrichment, which means they contain far fewer of the heavy elements present in younger stars like the Sun. Studying the chemical composition of these ancient stars, which can be done even at Andromeda's distance by analyzing the light they emit, tells astronomers something about the conditions in the galaxy's earliest epochs, before successive generations of stellar birth and death had built up the richer chemical environment that later stars formed within. For a long time, observations of Andromeda's center showed what appeared to be a double nucleus, two distinct concentrations of brightness at the core rather than one. This was interpreted by some astronomers as evidence that Andromeda might harbor two supermassive black holes at its center, possibly the remnant of an ancient merger between two galaxies, each bringing its own central black hole. The double nucleus hypothesis attracted significant attention and was taken seriously for some years. More recent and more detailed observations, however, have largely resolved the question. The current scientific consensus points to a single black hole surrounded by an asymmetric, off-center disk of stars, whose orbital distribution creates the appearance of two brightness peaks when viewed from our direction. The double structure is a geometric effect, a consequence of how stars are distributed in their orbits around the central mass, rather than evidence of two separate massive objects. The central bar structure of the galaxy connects the bulge to the inner disk. Bars are elongated concentrations of stars and gas that form through gravitational instabilities in rotating disks. Once formed, a bar acts as a kind of internal pump, redistributing angular momentum through the galaxy and channeling gas along its length. Gas can be funneled inward along the bar toward the central regions, which affects the rate at which material becomes available in the vicinity of the black hole and influences the pace of star formation near the core. Bars are common among spiral galaxies, present in roughly 2/3 of them, and their formation appears to be a natural stage in the evolution of a rotating disk system that has reached a certain level of mass and stability. The heart of Andromeda is ancient, dense, and quietly extreme. It has been accumulating mass and complexity for 12 billion years. The black hole at its center has grown through the consumption of gas and the mergers of smaller black holes over that entire span. The stars surrounding it carry within them the chemical record of every generation of stellar evolution that preceded them. And the whole structure continues turning slowly, the bar rotating through the inner disk, the bulge stars following their long elliptical orbits, the black hole sitting at the center of it all, waiting in the dark. Chapter 6: The Halo and What Surrounds the Visible Galaxy. What most people picture when they think of Andromeda is the bright disk, the spiral arms, the glowing central bulge, the overall shape of a galaxy seen at a slight angle from our position in space. That image, familiar from long exposure photographs, captures the densest and most luminous regions of the galaxy, but it does not capture most of what Andromeda actually is. The visible disk, as impressive as it is, represents only a fraction of the galaxy's true extent. Beyond its bright edges, extending outward in all directions into the surrounding darkness, lies a vast and largely invisible structure that dwarfs the disk it surrounds. This outer region is called the halo. Andromeda's stellar halo extends to at least 500,000 light-years from the galactic center. That is more than twice the radius of the bright visible disk. It is a roughly spherical distribution of stars and globular clusters, extremely diffuse compared to the disk, containing perhaps 1% of the galaxy's total stellar mass, but spread across a volume so enormous that the density of stars within it is incredibly low. A star in Andromeda's outer halo might be separated from its nearest neighbor by hundreds of light-years, rather than the few light-years typical of the solar neighborhood. The darkness between stars in that region is far deeper and more complete than anything experienced near the galactic center or in the disk. The stars in the halo are almost entirely old. Population 2 stars formed in the earliest phases of the galaxy's existence, when the universe was young and the interstellar medium had not yet been enriched by many generations of stellar death. They follow highly elliptical orbits that carry them far from the galactic plane before looping back inward, spending most of their time in the outer regions, but occasionally passing through the disk on the inward portion of their paths. Some of these stars have been traveling their current orbits for nearly as long as the galaxy has existed. They are fossils in a real sense, objects whose properties preserve information about conditions in the early universe that no longer exist anywhere we can directly observe. But the halo is not composed only of stars that formed within Andromeda itself. Much of its content, perhaps most of the substructure visible in deep photographic surveys, is the remnant of smaller galaxies that fell into Andromeda over billions of years and were torn apart by its gravitational forces. When a small galaxy or globular cluster ventures too close to a much larger galaxy, the difference in gravitational pull across the smaller object's diameter begins to stretch it. The near side is pulled more strongly than the far side, and the resulting tidal force elongates and eventually shreds the smaller structure. Its stars are pulled into long streams that follow the orbit the original object was traveling when it was disrupted. These streams of stars persist for billions of years before the orbital motions of the individual stars gradually spread them out and mix them into the general halo population. During the time when a stream is still coherent, still a recognizable ribbon of stars tracing an arc across the sky, it serves as a direct record of a past merger event. Andromeda's halo is full of these structures. Deep imaging surveys have mapped dozens of stellar streams, shells, and overdensities spread across the enormous volume surrounding the visible galaxy. Each one is the remains of something smaller that came too close. Some are the remnants of dwarf galaxies. Others are the debris of disrupted globular clusters. Together, they tell a story of ongoing growth through absorption. A large galaxy slowly accumulating mass by consuming the smaller objects that orbit it and that drift into its gravitational reach over time. Two of Andromeda's most prominent satellite galaxies are currently in various stages of this process. Messier 32 is a compact elliptical galaxy, sitting only about 24,000 light-years from Andromeda's center, a remarkably close position that places it well within the outer regions of the main galaxy's halo. It is small, roughly 8,000 light-years across, but it contains several billion stars and harbors at its own center, a supermassive black hole with a mass somewhere between 2 and 4 million solar masses. The fact that a galaxy, as small as Messier 32, contains a black hole of that mass suggests it may once have been considerably larger. A more substantial galaxy that lost much of its stellar mass during its close approach to Andromeda, stripped away by tidal forces over billions of years. What we see today may be the dense, resistant core of something that was once far more extended. Messier 110, the other large companion, orbits at a greater distance, roughly 170,000 light-years from the center, and is more spread out and diffused than Messier 32. It is a dwarf spheroidal galaxy, elongated in shape, and stellar streams connecting it to Andromeda are visible in deep photographs as faint trails extending across the surrounding space. These streams are stars that have already been pulled away from Messier 110 during its repeated passages through the outer regions of Andromeda's gravitational influence. They are no longer part of the dwarf galaxy. They have been captured into orbits around the larger galaxy and will eventually disperse into the general halo population. In a few billion years, Messier 110 will likely be completely disrupted, its remaining stars scattered and absorbed. Beyond these two prominent companions, Andromeda is accompanied by at least a dozen smaller satellite galaxies, dwarf spheroidals and ultra-faint dwarfs that are difficult to detect even with large telescopes because they contain so few stars and because those stars are spread across such large areas of sky. Some of these objects contain only thousands of stars. Many are dominated by dark matter to a degree that makes the visible stars almost incidental, traces of a much more massive invisible structure rather than the primary component of the system. These dark matter-dominated dwarfs are among the most extreme such objects known, and studying them provides information about dark matter that is difficult to obtain in any other way, precisely because the dark matter so completely dominates the visible matter that its properties are most clearly expressed. One notable feature of Andromeda's satellite system is that many of its companion galaxies orbit in a plane, a flattened arrangement rather than the random distribution in 3 dimensions that might be expected. This was initially puzzling when it was first mapped in detail. A random process of satellite capture over cosmic time would be expected to produce satellites distributed roughly spherically around the parent galaxy, not concentrated in a disk-like arrangement. The most widely accepted explanation at present is that the current satellite population formed largely from the debris of a single major merger event that occurred between 8 and 10 billion years ago. A large galaxy that fell into Andromeda was torn apart, and the material from that disruption, including the dwarf galaxies that condensed from it, inherited the orbital plane of the original intruder. If this explanation is correct, the planar arrangement of Andromeda's satellites is not a puzzle at all, but a fossil record of one specific ancient event preserved in orbital geometry across billions of years. The halo also contains hot ionized gas, material heated to temperatures of hundreds of thousands or millions of degrees by supernova explosions in the disk, and by the energy released as material falls into the galaxy's gravitational well. This hot gas is invisible to optical telescopes, but detectable in X-ray wavelengths. It fills the space between the visible stars and the outer boundary of the halo, representing a substantial reservoir of baryonic matter, normal matter made of protons and neutrons, that has been lifted out of the disk by energetic processes and now exists in a diffuse, extremely hot state far above the galactic plane. This material will eventually cool, fall back toward the disk, and contribute to future generations of star formation. It is part of the galaxy's long-term fuel supply, temporarily stored in an extreme state before returning to the cycle. The neutral hydrogen gas disk of Andromeda extends beyond the visible stellar disk, and radio telescope observations reveal that it is warped, one side tilted slightly away from the plane of the inner galaxy, the outer regions bent away from the flat geometry that characterizes the inner disk. This warping is common among spiral galaxies and is thought to result from gravitational interactions with companion galaxies, or from the accretion of material arriving along preferred directions from the surrounding intergalactic environment. The warp in Andromeda's outer gas disk is likely connected to both its merger history and the ongoing influence of its satellite galaxies, whose orbital motions exert a continuous gravitational tug on the outer regions of the disk. All of this, the stellar streams, the disrupted companions, the hot halo gas, the warped outer disk, describes a galaxy that is not a closed, self-contained structure, but an open system, continuously interacting with its environment, growing slowly by consuming smaller objects, losing material to its hot halo, and eventually recovering it. Andromeda is not static. It is part of a larger flow of matter and gravity that connects it to the surrounding space and to the smaller galaxies bound to it by mutual attraction. The bright disk is the most visible part of that system, but the halo is where most of the volume resides, where most of the history is written, and where the slow, ongoing process of galactic growth is most clearly expressed. Chapter 7. Dark Matter and the Invisible Architecture. There is more to Andromeda than can be seen. This statement is true in a straightforward observational sense. There are wavelengths of light the human eye cannot detect, and observations across the full electromagnetic spectrum reveal structures invisible to ordinary vision. but it is also true in a deeper and more fundamental sense. The majority of Andromeda's mass is not made of atoms at all. It does not emit light. It does not absorb light. It does not interact with electromagnetic radiation in any way that our instruments have yet detected. It makes itself known only through its gravitational influence on the matter we can observe, and that influence is unmistakable. This invisible component is called dark matter. The evidence for dark matter in galaxies like Andromeda comes most directly from measurements of how far stars and gas clouds orbit at different distances from the galactic center. In a system where all the mass is concentrated in the visible region, where the stars and gas account for essentially everything, the orbital speeds of objects in the outer disk should decline with distance from the center, in the same way that the outer planets of our solar system move more slowly in their orbits than the inner ones. This is a straightforward consequence of gravity. The further you are from the concentration of mass, the weaker the gravitational pull, and the slower the orbital speed required to maintain a stable orbit. This is not what astronomers observe in Andromeda, or in any other large spiral galaxy that has been measured carefully. Instead of declining in the outer regions, orbital speeds remain roughly constant, flat, far beyond the point where most of the visible mass is located. Stars and gas clouds in the outermost detectable regions of Andromeda's disk are moving at speeds that cannot be explained by the gravitational pull of the visible matter alone. Something else is exerting additional gravitational force, something with mass distributed through the outer regions of the galaxy and beyond, that does not show up in any image taken at any wavelength. The distribution required to produce the observed flat rotation curve is not a thin disk or a concentration at the center. It is an extended, roughly spherical halo, a cloud of invisible mass surrounding the visible galaxy and extending far beyond it in all directions. This dark matter halo encompasses the stellar halo, the gas halo, the satellite galaxies, and everything else associated with Andromeda. It reaches out to distances of at least 600,000 light-years from the galactic center, perhaps considerably further. Its total mass is far greater than the combined mass of all the visible stars, gas, and dust in the galaxy. For every unit of normal matter in Andromeda, every atom of hydrogen, every star, every grain of dust, there are roughly 5 or 6 times as much dark matter by mass. The visible galaxy, in other words, is a relatively small component of the total structure. The stars and gas that produce all the light, all the structure, all the complexity we observe are embedded within and surrounded by a much larger mass of something we cannot see and do not yet understand. The luminous galaxy is the minority partner in its own gravitational system. What dark matter actually is remains one of the most significant open questions in physics. It cannot be ordinary matter, protons, neutrons, electrons, the building blocks of atoms and everything made of them, because careful measurements of the abundances of light elements produced in the first few minutes after the Big Bang place strict limits on how much ordinary matter the universe can contain, and that limit falls well short of what would be needed to account for the gravitational effects attributed to dark matter. Whatever dark matter is, it is something beyond the standard inventory of particle physics as currently understood. Physicists have proposed numerous candidates. Weakly interacting massive particles, known as WIMPs, were for a long time the leading theoretical candidate. Hypothetical particles with masses in the range of tens to hundreds of times the proton mass, interacting with ordinary matter only through gravity and the weak nuclear force. Experiments designed to detect WIMPs directly, placed deep underground to shield them from cosmic radiation, have been running for decades without a confirmed detection. Axions are another candidate. Extremely light particles originally proposed to solve a different problem in particle physics, but which would also have the right properties to constitute dark matter if they exist in sufficient numbers. Sterile neutrinos have been proposed. Primordial black holes formed in the very early universe before any stars existed, have been considered and constrained by various observations, though not entirely ruled out. None of these candidates has been confirmed. The nature of dark matter remains unknown. What is known, with considerable certainty, is that something with the gravitational properties of dark matter exists, that it surrounds and permeates galaxies, and that without it the structure of the universe as we observe it could not have formed. This last point is important. Dark matter is not simply a correction applied to make rotation curves work out. It is, according to our current understanding of cosmology, the primary agent of structure formation in the universe. In the very early universe, shortly after the Big Bang, the distribution of matter was almost perfectly uniform. A nearly smooth sea of hydrogen and helium with only tiny variations in density from place to place. Those tiny variations were the seeds of everything that exists today. Over hundreds of millions of years, gravity amplified the slightly denser regions, drawing surrounding matter toward them. The first structures to collapse under gravity and become gravitationally bound were dark matter halos, clumps of dark matter that formed before ordinary matter had cooled and condensed enough to follow. Ordinary matter then fell into those pre-existing dark matter halos, cooled further by radiating energy, and eventually collapsed enough to form the first stars. Andromeda, like every other large galaxy, formed within a dark matter halo. The halo was there first, providing the gravitational scaffolding into which gas fell and accumulated. Without that scaffolding, the gas would not have concentrated in the same way, and the galaxy as we know it would not exist. In this sense, the invisible architecture of dark matter is not merely an accessory to the visible galaxy. It is the foundation on which the galaxy was built and within which it continues to exist. The dark matter halo surrounding Andromeda is not a perfectly smooth, featureless sphere. Computer simulations of dark matter halo formation predict that halos should be lumpy on small scales, containing numerous smaller concentrations of dark matter distributed throughout the larger halo. These smaller concentrations are the dark matter equivalents of the satellite galaxies we observe orbiting Andromeda. Some of them contain enough ordinary matter to have formed stars, and those are the visible dwarf galaxies we have catalogued. Others may contain little or no ordinary matter. Dark satellites, essentially invisible structures whose presence can only be inferred indirectly from their gravitational effects on surrounding material. Detecting these dark satellites is one of the significant challenges in observational astronomy. Their existence is predicted by the standard cosmological model, but confirming them observationally requires techniques that can identify gravitational effects without any accompanying light. Gravitational lensing, the bending of light from background sources by foreground mass concentrations, provides one approach, and ongoing surveys are working to map the small-scale structure of the dark matter distribution around nearby galaxies, including Andromeda. The flat rotation curve of Andromeda, the evidence that first pointed toward dark matter's presence, was measured by tracking the velocities of gas clouds at different distances from the galactic center, using radio telescope observations of the hydrogen emission line. That measurement was not made once and accepted. It was repeated, refined, and extended to greater distances over decades of work by multiple research groups using different instruments and different techniques. The result has been consistent. The dark matter is there. The halo is real. The visible galaxy is embedded within something far larger that we cannot see. This is the invisible architecture of Andromeda, the structure that holds everything else in place, that shaped the galaxy's formation, that governs the orbits of its satellite galaxies, and that will determine how the galaxy continues to evolve over the billions of years to come. It surrounds the light without producing any of its own. It constitutes the majority of the mass without being detectable by any telescope we have yet built. And it remains, despite decades of dedicated effort to understand it, fundamentally mysterious. Chapter 8. The Slow Approach. There is a fact about Andromeda that is not often given the attention it deserves, perhaps because its implications unfold on timescales so far beyond ordinary human experience that they are difficult to connect to anything felt as immediate. Andromeda and the Milky Way are moving toward each other, not drifting, not oscillating, moving toward each other on a trajectory that, barring some currently undetected factor that would alter the calculation, will eventually bring the two galaxies into direct contact. The closing speed is approximately 110 kilometers per second. That is roughly 400,000 kilometers per hour, or about 250,000 miles per hour, a speed at which you could circle the Earth's equator in just over 6 minutes. By any standard of ordinary human experience, it is an extraordinary velocity, and yet, across a distance of 2.5 million light-years, it amounts to almost nothing on any timescale a human lifetime can encompass. Each year, the gap between the two galaxies closes by a distance of roughly 3.5 billion kilometers, less than the distance from the Sun to Neptune. Each million years, the separation decreases by approximately 100 light-years. Watching this approach from a human perspective would be like watching a glacier move, except immeasurably slower. The change is real and measurable and consistent, but it is change operating on a scale that makes the entire span of recorded human history invisible. The first close encounter between Andromeda and the Milky Way is estimated to occur in approximately 4.5 billion years. At that point, the two galaxies will interpenetrate, passing through each other in an event that, despite the word collision, will involve almost no direct contact between individual stars. This is because the stars within both galaxies, despite their enormous numbers, are separated from each other by distances so vast that two galaxies can pass through one another without any two stars actually touching. The space between stars is not empty in a chemical sense. There is gas and dust and cosmic radiation throughout. But it is empty in the structural sense that matters here. The probability of any two specific stars colliding during the merger of Andromeda and the Milky Way is essentially zero. What will collide with genuine violence is the gas, the interstellar medium of both galaxies, the clouds of hydrogen and helium and dust distributed between the stars, will meet and compress as the two disk systems overlap. Gas clouds moving in different directions will slam into each other at high relative velocities, shocking and heating the material. The compressions produced by these collisions will trigger bursts of star formation on a scale that neither galaxy currently experiences. New stars will ignite across the merging system in numbers that dwarf the current rate of roughly 1 solar mass per year in each galaxy. The burst will be temporary. It will exhaust available gas reserves rapidly, but while it lasts, it will produce a spectacular concentration of young, massive, luminous stars blazing across the disturbed structure. The gravitational interaction during the first passage will distort both galaxies profoundly. The orderly spiral structures of each, the flat rotating disks, the arms of higher density winding outward from the central bars, will be disrupted. Long tidal tails of stars will be drawn outward from both galaxies as the gravitational fields of each pull on the outer regions of the other. These tails will stretch for hundreds of thousands of light years, rivers of stars streaming outward into the surrounding intergalactic space. The two galaxies will look nothing like the structures they are today. After the first passage, the two systems will separate again. Their velocities at the moment of encounter will carry them apart, but mutual gravitational attraction will slow that separation, halt it, and then reverse it. The galaxies will fall back toward each other for a second encounter, then a third. Each successive passage will scatter the stellar orbits further from their original configurations and consume more gas in additional bursts of star formation. Computer simulations of this process, which have been run many times using increasingly sophisticated models of both galaxies, suggest that the merger will proceed through multiple passages over a period of several billion years following the first encounter, before the two systems finally lose enough energy to their mutual gravitational interaction to settle into a single merged structure. The end product will not resemble either parent. When two large spiral galaxies merge, the orderly rotation that maintains the disk structure of each is disrupted beyond recovery. The stars from both galaxies, which were originally moving in roughly organized patterns within their respective disks, get scattered onto orbits with random orientations. The result is a spheroidal distribution, a roughly elliptical shape without the flat disk and spiral arms that characterize the parent galaxies. The merged system will be a giant elliptical galaxy, its stars distributed in a smooth, rounded cloud rather than a structured disk. Astronomers have playfully given this future object a name, Milkomeda, or sometimes Milkdromeda. Though the name is informal and the object itself will not exist for billions of years yet, star formation in the merged galaxy will decline sharply after the merger completes. The violent gravitational interactions during the merger will heat the remaining gas, making it too diffuse and turbulent to collapse easily into new stars. Without ongoing star formation to continually produce new young blue stars, the stellar population of the merged galaxy will gradually age. The most massive stars will have already died during the merger itself, or in the starbursts it triggered. What remains will be progressively older, cooler, redder stars. The population that characterizes elliptical galaxies, which astronomers sometimes describe as red and dead, in the sense of being composed primarily of aging stars with little new stellar birth occurring. The two supermassive black holes, Andromeda's central black hole at 140 million solar masses, and the Milky Way's Sagittarius A star at 4 million solar masses, will follow a different trajectory through this process. As the galaxies merge and the stars of both systems scatter into the spheroidal distribution of the merged galaxy, the two black holes will sink toward the center of the combined structure through a process called dynamical friction. Moving through a sea of stars, each black hole gravitationally accelerates the stars it passes, transferring momentum to them and losing momentum itself. This loss of momentum causes each black hole to spiral gradually inward toward the center of mass of the merged system. Eventually, the two black holes will find themselves in close proximity, orbiting each other as a binary system. At that point, their further approach will be driven by the emission of gravitational waves, ripples in the fabric of space-time produced by the acceleration of massive objects. Gravitational waves carry energy and angular momentum away from the binary system, causing the two black holes to spiral closer together. The process accelerates as the separation decreases, until in a final event lasting perhaps only a few minutes, the two black holes merge into a single object with a mass equal to the combined total of both, minus a small fraction radiated away as gravitational waves. That merger will release more energy in gravitational waves than the combined electromagnetic output of all the stars in the observable universe during the same brief interval. The space-time distortion produced will propagate outward from the merged galaxy at the speed of light, detectable in principle by any gravitational wave observatory within range. What it will leave behind is a single supermassive black hole at the center of Milky quiet, massive, carrying within its properties the history of two separate galactic nuclei that took 4.5 billion years to find each other. The fate of Earth during all of this is uncertain in its details, but not necessarily catastrophic in the immediate sense. The Sun will have entered its red giant phase before the merger begins, expanding to engulf the inner planets and making Earth uninhabitable in any case that relates to life as it currently exists. Whether Earth survives as a physical object through the merger is a question of orbital mechanics. Whether the gravitational perturbations of the encounter shift its orbit enough to eject it from the system, or alter its relationship to the aging Sun in ways that matter. It may survive. It may be flung into the outer reaches of the merged system. The question is interesting but not urgent on any timescale relevant to the present. What is perhaps most worth sitting with in all of this is not the violence of the eventual merger, but the patience of the approach. The two galaxies have been moving toward each other for a very long time already, for most of the age of the universe, closing a gap of 2.5 million light-years, 100 kilometers per second at a time. The merger is a consequence of the same gravitational binding that makes the local group of galaxies a coherent structure. The same mutual attraction that has kept Andromeda and the Milky Way as gravitational companions across all of cosmic history. The collision, when it finally comes, will be the culmination of a relationship between two galaxies that has existed for as long as either of them has. Chapter 9. What we can and cannot know. There is a particular quality to our knowledge of Andromeda that is worth thinking about carefully, because it is different in kind from most of the knowledge we accumulate about the world around us. When we study something close, a rock, a plant, the weather, even the sun, we are working with information that is current, or nearly so. The gap between the state of the thing and our observation of it is negligible. But with Andromeda, every observation we make is an observation of the past, not the recent past, the deep past. The light we receive from it left its source 2.5 million years ago, and there is no way to receive anything more recent. The present state of Andromeda is, in a strict and irreducible sense, unknowable to us. This is not a technological limitation. It is not a problem that better telescopes or more sensitive instruments will eventually solve. It is a consequence of the finite speed of light, which is the speed at which all information travels through space. No signal of any kind, not light, not radio waves, not any form of electromagnetic radiation, not gravitational waves, can travel faster than light. Whatever is happening in Andromeda at this moment in its own reference frame will not be detectable from Earth for another 2.5 million years. The galaxy is continuing to evolve. Stars are continuing to be born and die. Its satellite galaxies are continuing their slow orbital approach. All of this is happening in Andromeda's present, and we will not witness any of it for a span of time that makes the entire history of our species look brief. What this means practically is that we are studying a snapshot, a very detailed snapshot, captured across many wavelengths and refined over a century of increasingly sophisticated observation, but a snapshot nonetheless. The Andromeda we know is the Andromeda of 2.5 million years ago. We can reason about its current state by extrapolating from what we know about galactic evolution, applying the physical laws that govern how stars age and galaxies change over time. But we cannot observe it directly. This constraint shapes everything about what we know and do not know. What we know well is the large-scale structure, the overall size of the galaxy, its mass, its distance, the distribution of its stellar populations across the disk and bulge and halo. These are measured with reasonable precision and confidence. The methods used to determine them have been cross-checked against each other and against observations of other galaxies. The distance measurement, as we discussed earlier, rests on a careful chain of calibrations that has been refined over decades. The mass estimates incorporate data from stellar dynamics, gas rotation, and the motions of satellite galaxies. The structural measurements come from imaging across multiple wavelengths. None of these measurements is perfect, but each has known uncertainties that are understood and accounted for. What we know less well is the fine detail. Individual stars in Andromeda's disk are resolved by the most powerful space-based telescopes. The Hubble Space Telescope has imaged sections of Andromeda's disk and resolved more than 100 million individual stars in those regions, allowing measurements of their brightnesses and colors that reveal their ages and chemical compositions. But even this extraordinary achievement covers only a portion of the galaxy. The full disk contains approximately 1 trillion stars, and resolving all of them individually is far beyond any instrument that exists or is currently planned. The faint stars are particularly difficult. Red dwarfs, the most numerous type of star in Andromeda, as in all galaxies, are individually too dim to detect at this distance, except in the most nearby and favorable circumstances. We infer their presence from the overall mass and luminosity of the galaxy, rather than counting them directly. The white dwarfs, neutron stars, and stellar mass black holes that are the remnants of previous generations of stars are similarly invisible, unless they happen to be in binary systems, where interactions with a companion produce detectable radiation. The population of stellar remnants in Andromeda is inferred rather than observed. Planets are entirely beyond our current reach. The methods used to detect planets around nearby stars, measuring the tiny dimming of a star's light as a planet passes in front of it, or the slight wobble in a star's motion produced by a planet's gravitational pull, require a level of precision that cannot be achieved for stars 2.5 million light-years away. The angular separations involved are immeasurably small. The brightness variations produced by a transiting planet are swamped by noise. Even the James Webb Space Telescope, the most capable observatory humanity has yet placed in space, cannot detect individual planets in Andromeda. Everything we know about the planetary population of Andromeda is inferred from what we know about planet formation and from the statistics of planetary systems observed in our own galaxy. This is a significant limitation because planets are where the most interesting questions about Andromeda ultimately lead. Whether life exists somewhere in that galaxy, whether among its trillion stars and the countless worlds orbiting them, there are any places where chemistry has organized itself into something that metabolizes and reproduces and eventually thinks, is a question we cannot answer and may never be able to answer from our position. We can reason about it. Given what we know about the abundance of potentially habitable planets in our own galaxy, and given the much larger stellar population of Andromeda, The statistical argument for life existing there somewhere is strong, but statistics are not confirmation. The universe has surprised us before by being less hospitable than naive calculations suggested, and it has surprised us by being more hospitable than expected. Without direct observation, we do not know. What we also cannot know with certainty is Andromeda's precise future. The merger with the Milky Way is well enough established. The closing velocity has been measured, the trajectory has been calculated, and the outcome predicted by simulation. But the details of how the merger will proceed depend on factors that are not perfectly constrained. The exact three-dimensional velocity of Andromeda relative to the Milky Way, including any component of motion perpendicular to the line connecting the two galaxies, affects the geometry of the encounter significantly. Measurements of this transverse velocity have been made using observations from the Hubble Space Telescope, tracking the positions of stars in Andromeda over years to detect any systematic drift across the sky. The results suggest the transverse component of the velocity is small relative to the radial component, meaning the galaxies are approaching nearly head-on rather than on a grazing trajectory. But the measurement has uncertainties, and those uncertainties propagate into the predicted details of the merger. There is also much we do not know about Andromeda's past. The stellar streams in the halo preserve some record of past mergers, and astronomers have worked to reconstruct which features correspond to which ancient events. The major merger that disrupted Andromeda's disk, approximately 800 million years ago, has left detectable signatures in the asymmetry of the spiral structure and in the distribution of stars in the inner halo. The event that likely produced the planar arrangement of satellite galaxies happened between 8 and 10 billion years ago. But the full merger history of the galaxy, every significant interaction it has experienced across 12 billion years, cannot be recovered from what we observe today. Information is lost as stellar streams phase mix into the general halo population, and as the signatures of ancient events become too diffuse and smooth to distinguish from the background. What we have then is a partial picture, rich in some areas, sparse in others, constrained at both ends by the limits of what can be observed from a single location 2.5 million light-years away, looking at light that left its source before our species existed. The picture is remarkable in what it contains. The distance measured to within a few percent, the mass estimated to within a factor of 2, the structural features mapped across the electromagnetic spectrum, the merger history partially reconstructed from faint stellar streams. A century ago, astronomers did not know whether Andromeda was a nearby gas cloud or a separate galaxy. Now we know its distance, its composition, its age, its future. That is an extraordinary progression, but the limits are real. Andromeda keeps its finest details to itself. The planets are invisible. The life, if any exists, is undetectable. The present state of the galaxy is permanently inaccessible. We study it from our position in space and time, with the instruments and methods available to us, and we learn as much as those constraints allow. What lies beyond those constraints? The present Andromeda, the planets, the possible life, the full complexity of 1 trillion stellar systems, exists whether or not we can observe it, and reminds us that the universe is not obliged to make itself fully legible to any observer within it. There is something genuinely restful in that. The unknown is not a failure. It is simply the honest boundary of what is reachable from where we stand. Chapter 10. What Andromeda means. There is a final way of thinking about Andromeda that goes beyond the measurements and the structures and the timescales, though it depends on all of them. It is the question of what it means to know that something like this exists, what it does to a person's sense of scale and place and time, to genuinely sit with the reality of a galaxy 2.5 million light-years away, containing 1 trillion stars, 12 billion years old, moving slowly toward the one we live in. This is not a scientific question. It does not have a quantitative answer. But it is worth taking seriously, because the knowledge we have assembled about Andromeda is not merely technical. It is knowledge about the context in which every human life has ever been lived, and about the nature of the universe that contains us. Begin with the light itself. When you look at Andromeda on a dark, clear night, when you find that faint, elongated smudge in the constellation that shares its name, and allow your eye to rest on it, the photons entering your eye have been traveling for 2.5 million years to reach you. They left their source before modern humans existed. They crossed 2.5 million light-years of intergalactic space, a void containing almost nothing. No stars, no planets, no gas worth speaking of, just the occasional stray atom and the faint background radiation of the early universe, and arrived at your eye at this particular moment, on this particular night, to form this particular impression of a faint smudge of light. The fact that they arrived now, rather than a second earlier or later, and that you were looking in that direction to receive them, is a coincidence so small against the backdrop of cosmic time that it barely registers. And yet it happened. Those photons carry within them information about a structure containing 1 trillion stars. Each photon was emitted by a specific star in a specific region of Andromeda, traveled outward from that star in all directions simultaneously, and this particular photon happened to be traveling in exactly the right direction to reach Earth 2.5 million years later. The vast majority of photons emitted by any star in Andromeda travel outward into space in directions that will never intersect any other object. They will continue outward forever, or until the universe ends, carrying their information into permanent emptiness. The ones that reach your eye are the exceptions, the rare fraction of an enormous emission that happen to be aimed, in the broadest possible sense, in your direction. This is true of every star you have ever seen. But with Andromeda, the numbers are so much larger and the distance so much greater that the fact becomes harder to look past. Consider also what Andromeda is made of. The stars in Andromeda are composed of the same elements as the stars in the Milky Way. The hydrogen, helium, carbon, oxygen, iron, and every other element present in Andromeda's stellar populations were produced by the same processes. Primordial nucleosynthesis in the first minutes after the Big Bang, and stellar nucleosynthesis in the cores of successive generations of stars over billions of years. The laws of nuclear physics that govern those processes are the same everywhere in the observable universe. The same quantum mechanics, the same gravitational dynamics, the same thermodynamics apply in Andromeda as apply here. The atoms in your body were forged in stars. This is not a poetic approximation. The carbon in every cell, the oxygen in every breath, the calcium in every bone. These elements were produced inside stars that lived and died before the sun formed, and they were scattered into the interstellar medium by stellar winds and supernova explosions, and they were eventually incorporated into the cloud of gas and dust that collapsed to form the solar system, and from that material the Earth formed, and from that material life arose, and here you are. The atoms that constitute you were processed through stellar interiors before they reached you. The atoms in Andromeda's stars went through the same process. They are made of the same stuff, assembled by the same physics. In this sense, Andromeda is not foreign. It is not alien in any fundamental way. It is another expression of the same matter and the same laws that produced everything you have ever encountered. What separates us from it is distance and time, both of which are enormous. But neither distance nor time changes what things are made of or what laws govern them. The universe is, in this sense, deeply consistent. Andromeda obeys the same rules as everything else. Its stars burn by the same mechanism as our sun. Its black holes curve spacetime according to the same equations. Its dark matter halos formed through the same gravitational amplification of early density fluctuations. It is distant and vast, but it is not strange. Think also about the timescales. Andromeda has been forming stars for approximately 12 billion years. The universe itself is approximately 13.8 billion years old. Andromeda formed when the universe was less than 2 billion years old, when the cosmic structures we see today were still assembling themselves from the aftermath of the Big Bang, when the first generations of stars were already living and dying and enriching the interstellar medium with the elements that would make later generations possible. The galaxy we observe today is the product of 12 billion years of continuous stellar birth and death, of mergers with smaller galaxies, of slow chemical enrichment, of the gradual build-up of complexity from simpler beginnings. Against that backdrop, the entire span of human existence is a thin line at the very end of a very long history. The earliest members of our genus appeared roughly 2.5 million years ago, a figure that, not coincidentally, is the same as the distance to Andromeda in light years. The light we receive from Andromeda tonight has been traveling for exactly as long as our genus has existed. Everything that has happened in human prehistory and history, every generation, every migration, every development of language and technology and art and science has occurred during the transit time of that light. 12 billion years of Andromeda's existence, and the last 2.5 million of them are the ones during which the light currently reaching us was in transit. The other 9.5 billion years of the galaxy's history are further in the past than the light we receive can show us. If you wanted to observe Andromeda as it was when it first formed, you would need to wait 9.5 billion years for that ancient light to arrive. It is on its way. It has been traveling for 9.5 billion years already and has not yet reached us. The universe contains no shortage of this kind of number. Figures so large that they exceed anything human intuition was built to handle. We evolved to navigate a world measured in meters and years, to track objects moving at speeds measurable in kilometers per hour, to plan across timescales of days and seasons and lifetimes. Nothing in that evolutionary history prepared us for light years or billions of years, or the gravitational dynamics of galaxy clusters. And yet, here we are, having assembled the tools and the reasoning to measure these things, to understand the processes that produce them, and to place ourselves accurately within the picture they describe. That is worth sitting with on its own terms. The capacity to understand Andromeda, to measure its distance, to map its structure, to trace the lives of its stars, to calculate its future, is itself an extraordinary feature of the universe. The universe has produced, in at least one location, observers capable of comprehending it on scales that dwarf the observers by every conceivable measure. Whether this has happened elsewhere, in Andromeda itself, on some planet orbiting some star in its spiral arms, where some form of conscious life has developed the curiosity and the tools to look outward and wonder about the galaxy it inhabits and the faint smudge of light in its own sky that is the Milky Way. We do not know. The distance makes confirmation impossible, but the possibility is not unreasonable, and there is something quietly moving about it. two galaxies separated by 2.5 million light-years, each potentially containing observers who have looked across the intergalactic void at each other's home and spent long, unhurried hours trying to understand what they are seeing. Andromeda will be there tonight when the sky is dark enough and the conditions are right. It will appear as it always has. A faint, soft smudge of light, easy to overlook, easy to mistake for nothing in particular. But you will know, if you have traveled this far tonight, what that smudge actually is. 1 trillion stars, 12 billion years of history, 2.5 million light-years of empty space, a structure larger than anything else in our local corner of the universe, moving slowly toward us, carrying within it the same matter and the same physics, and perhaps even the same questions that we carry here. The universe is not a small place, but it is, in the ways that matter most, a consistent one. The same rules apply everywhere. The same matter appears everywhere. The same processes, gravity, nuclear fusion, the slow drift of gas into stars and stars into death and death back into gas, operate everywhere. Andromeda is not an exception to the universe. It is an expression of it, on a scale that asks us to expand what we think we mean by the word large, and to sit quietly with the answer. If tonight was a good companion, a like or a subscribe helps other curious minds find their way here.